Okay, so if there's your probability rules. We're going to go over that today. Complement rule, introduce that to you. Addition rule, it's mutually exclusive and it's disjointed. Okay, so the first rule is that you know that the probability of any event is between 0 and 1, meaning that we can have we can have 0 and we can have 1. You just can't have them together. Okay? All right. Number 2, all possible outcomes added together is 1. Okay? So just easy peasy. So rolling a fair die, let's make it 6-sided. So our outcomes are going to be 1, 2, 3, 4, 5, and 6. And then we also know that the outcome for each one is going to be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, and 1, 6. Okay. Now added those together gives us 6 out of 6, which is 1. Now with decimals, you're going to have to be careful. All right, because obviously you're going to have rounding error. You're going to have that little either you're going to be above 1 or below 1. So you're going to have to account for that error, okay? But you can use decimals. You see it all the time, okay? Next one's long, so I'm going to pause it. So 3 says if all outcomes in the sample space, remember I can just write capital S for the sample space, are equally likely, the probability that event A occur can be found using the formula, basically what you guys have been doing for probability for years, okay? So what this means is that equally likely is that there's a fair chance that it's going to happen, that you could roll the dice, okay? We tie that into independence, that the roll before it or the card draw before it, anything like that, doesn't affect our current draw. So they're going to be independent from one another, okay? Okay. Number 4, this is our complement rule. All right, and in this complement rule, what we're looking at is this is the opposite of the event happening. So an example is going to be if my event A was to draw a heart, then my complement, which is shown like that, A with my exponent as the letter C, the complement of A is not to draw a heart. Okay, so sometimes you get a long list of outcomes and it'll be easier to go, okay, it's going to be easier for me to find out what not to do, okay, instead of trying to figure out how to do the other way, okay? So what we're going to do is we're going to go, I'm going to write the words. So we're going to go 1 minus the event A is equal to the complement, okay? So it will look something like 1 minus, see here, not to draw a heart. So that means we want everything that's not a heart. So if we say, okay, well, the heart is 13 out of 52, right? So then 1 minus, that's going to be 52 minus 13 is going to be 39 out of 52. That's 39. Okay, so that's what we're looking at. Complement rule, it helps us out when things are long and nasty. Okay, all right. So 5, I'm going to pause it after I write this. 5 is we're going to introduce mutually exclusive. Also known as being disjointed. Okay. All right, so real quick, the mutually exclusives is if two events have no outcomes in common, the probability that one or the other is the sum of the individual probabilities. So for our formula is going to be P, A, or B is equal to PA, the probability of A plus the probability of B. What it looks like is this, is if I have a Venn diagram, I've got the event A and the event B here, okay? So then the drawing the heart is going to be A, rolling a 6 is going to be B. I understand that there is a 6 of hearts, but I don't care about that right now. All I care about is drawing a heart, okay? So then I'm going to go the probability of A, which is 13 out of 52. Probability B is 1/6. So then I'm going to go 5 5/12, which is approximately 0.42. Okay. Sweet. All right. So what we're going to work on now is we're going to do some examples. Okay. Nope. Yeah, that's really high. If you want to know the probability of drawing just a 6 of hearts, is going to be 1 out of 52. But this is saying, here, let me pause the video real quick. This is going to be our examples. The first thing we're going to look at is 39. Role-playing games, computer games in which the player takes the roles of characters are very popular. They go back to the earlier tabletop games such as Dungeons and Dragons. These games use many different types of dice. A 4-sided die has sides with 1, 2, 3, and 4 spots. List the sample space for rolling the die twice, spots showing on first and second rolls, and then what is the assignment or probability outcomes in the sample space. Assume that the die is perfectly balanced, meaning that it's fair, it's not loaded, anything like that, okay? So 39, you have, I'm just gonna do it like this. I've got die 1 that has 1, 2, 3, and 4. Kind of like what we did yesterday. We've got second die that does this. So this is going to be 1, 1. This is going to be 1, 2. This would be 1, 3. And this would be 1, 4. And then I'm going to pause it and let you guys finish it. So this is our sample space. This is our possible outcomes. And then the part B was like, what is the assignment of the probability to outcomes in the sample space, right? So that means that what's the probability of getting this space right here? Well, how many total are there? There's 16, so it'd be 1 out of 16. Because it told us that each one of these is an equally likely outcome. They're not loaded, they're not going to screw us over, anything like that, but it's balanced, okay? Do you guys have any questions? 41 says, role-playing games, refer to exercise 39, define event A, the sum is 5, and then find the probability of A. Well, let's look at this real quick. So what we're going to practice, what you guys are going to see is this is my event, so I'm going to say let A equal that we roll the sum of 5, right? So then when it says find the probability of A, I have 16 as my total outcome, and then I want sum of 5. The cool thing, cool thing about the dice is that if you make your table correctly, you can see the diagonal, that this whole diagonal right here is 5. And so then you're going to go 1, 2, 3, 4, put the 4 there, which reduces to 1/4, which is 0.25. All right. Now the question is going to be, well, what answer is correct? Well, if you have a fraction, you want it to simplify it, you want to simplify it, all right? If it's asking you to find it as a percent, you're going to want it as a percent. You're going as a decimal, okay? So you've just got to be able to understand what we're asking for, and it's usually straightforward, okay? I'm not going to ding you because personally I think the fractions are easier to work with because it gives you that exact number and you're not going to have to round. You're not going to have that rounding error, okay? But depending on, again, depending on what you're asking for, that's what we're going to work with, okay? So we're going to go to 43 next. So 43A gives us this, that you roll a six-sided die. These were the outcomes or the probabilities that they listed, all right? Basically what happened is they kept track of their rolls like this. Reason why we know it's 6 is because the smallest fraction we have is 1/6, so that means that there's 6 total outcomes. So then we roll these out and we add the numerators together, it gives 6/6/1, which makes this legitimate. Okay? Oh, we got to do part B. Part B says, choose a college student at random and record gender and enrollment status. So probability of female, I'll let you read all that, but add those together real quick. And what do you know? If you had 56 and 44 together, what do you get? 56, 44 is 1. So if you add these two together, what happens? It's over 1. So is this legitimate? That's how you know, okay? So part B is illegitimate. There's a whole joke right there, but we won't go there. All right, now, dealing a card from a shuffled deck. Notice they didn't say that it was a fair deck, right? Because if you look, you've got 12 clubs, 12 diamonds, 12 hearts, and 16 spades. But guess what happens when you add all those together? You want to bet? You want to bet $1? Yeah, it adds up to 1, so that means that it's legitimate, yeah. It's bad, but is legitimate. So here's 45. Basically what we have is blood type from Black Americans, and they want to know the probability that they gave us. The probability of O is 0.49, probability of A is 0.27, the probability of 0.20. The question is, how would you do, or how would you find that? Yep. What's that called? Nope. Complement rule. So you would say, I would use the complement rule. Yep. And so that's found by just doing what Zane said, but you've got to state what rule you're using. Okay. So you do that. And if you do it correctly, you should get okay. We talked about how to find, we did the complement rule to find this. And then I'm introducing how do we going to do the addition rule. So the probability of having an O type plus the probability of having a B type, which would be 0.69. Okay, easy peasy stuff. This first little bit's nice, straightforward. Okay. All right, so last question I'm going to give you guys to kind of practice. I'm going to pause it so we can. Okay, so here's my data set. I'll let you read it because we're running short of time. So basically the questions are, what is the probability for event C, because I didn't give you that. Are the events mutually exclusive? And then find the probability of A or D, okay? Blank screen. All right, so real quick for the answers, C is 0.28. Yes, they're mutually exclusive because they don't overlap, no fluff. And then the probability of A or D is equal to 0.13 plus 0.30, which is 0.43, okay? Yeah,